I'm gonna start. Just keep going. Ready? Why, hello there. Today we're going over chemical bonding. A chemical bond is a bond that holds two or more atoms or ions together.
Wait, there are 3 types of bonds, right?
Yes, you're right. There are 3 general types of bonding: covalent, ionic, and metallic. Covalent bonding occurs due to electronegativity. When the electronegativities of 2 atoms differ, then it leads to a different type of covalent bond. In addition to those things, we'll also be talking about the octet rule, Lewis and resonance structures, and finally, the strengths and lengths of covalent bonds.
I'm going to teach you guys how to study this chapter. As with any other chapter, you're going to want to take notes. Although notes can be tedious and annoying, they are crucial for understanding the concepts. Some things to remember when taking notes is to highlight bolded words and look at the figures.
Hey Darlene, do you want some?
Yeah, sure. Another great thing to remember is to have some snacks with you. This can really help your thought process, or at least it helps mine. Let's jump in!
So, today I'll be teaching you about Lewis symbols and the octet rule. The Lewis symbol for an element, chemical symbol, and a dot for each valence electron. Valence electrons are the electrons in the outermost occupied shell of an atom. The octet rule explains an atom's tendency to gain, lose, or share electrons until they are surrounded by 8 valence electrons.
Sulfur has the electron configuration Ne3s2 3p4 and therefore has 6 valence electrons. The dots are placed on the 4 sides of the symbol, top, bottom, left, and right, and each can hold up to 2 electrons.
Next, we will go over ionic bonding. Ionic substances result from the interaction of metals on the left side of the periodic table with non-metals on the right side. An example of ionic bonding is the combining of sodium metal with chlorine gas to create sodium chloride. Ionic substances are usually brittle and crystalline with high melting points. Ionic compounds are stable due to the attraction between ions of opposite charge, which form a lattice. Lattice energy is the energy required to separate 1 mole of a solid ionic compound into its gaseous ions. Lattice energy increases as the charge on the ions increase and the radii decrease.
In the reaction between sodium and chlorine, there is an electron transfer from the sodium atom to the chlorine atom. The electron transfer has to do with ionization energy, which is how easily an electron can be removed from an atom, and electron affinity, which measures how much an atom wants to gain an electron. In the reaction, sodium loses an electron, while chlorine gains an electron. Many ions tend to have noble gas configurations. In other words, ions have the same electron configuration as a noble gas. Sodium uses 1 electron to form Na+, which has the same electron configuration as neon. As you can see, Na loses the 3s1 to create Na+, leaving Ne. There are exceptions to the electron configurations of transition metals. In forming ions, transition metals lose the valence shell s electrons first, then it loses as many d electrons required to reach the charge of the ion. Let's take a look at the formation of Fe2 from Fe. When forming Fe2+, the 2 4s electrons are lost from Fe.
Now we're going to talk about covalent bonding. There are many substances that don't have the necessary characteristics of ionics. Because of this, G and Lewis stated that the atoms in these substances might be able to attain their full electron configuration through sharing. This sharing would be referred to as covalent bonding. To get a picture of how covalent bonding can help an atom achieve electron configuration, Lewis structures were created. Lewis structures or Lewis dot structures are representatives of the bonds shared between the 2 atoms. In the next scene, I will demonstrate how to depict them correctly. So we know that oxygen has 6 electrons and carbon has 4 electrons. So this means that in the end, we should have a total of 16 valence electrons. All right. Also, we need to have an octet for each of these 3 atoms. So if you look closely at the diagram, you will see that we have 4 lone electrons by themselves. Now, to not make them by themselves, we're going to bring them to the inside. And by doing this, we will make another bond, and also we will have the octet that we need. So it should look something like this. And basically, if you come back up here, what we did is we just brought in these 2 electrons that were on the outside, and then having 2 of them makes a pair, makes another bond, so we have our double bond, and this is the final diagram. And if you count each electron, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 electrons, and that is the Lewis structure for CO2. When writing Lewis structures, remember you are showing the valence electrons, then the rest should be the remaining number of dots needed to reach an octet. Depending on the number of shared electron pairs there is, the atoms will form either a single, double, or triple bond.
This section is about bond polarity and electronegativity. Bond polarity is how equally or unequally the electrons in any covalent bond are shared. In a nonpolar covalent bond, the electrons are shared equally, whereas in a polar covalent bond, one of the atoms exerts a greater attraction for the bonding electrons than the other. An ionic bond is formed when the difference in relative ability to attract electrons is large enough. To estimate whether a given bond is nonpolar covalent, polar covalent, or ionic, we use a quantity called electronegativity. Electronegativity is the ability of an atom in a molecule to attract electrons to itself. This means the more electronegative an atom is, the greater its ability to attract electrons. Electronegativity values are based on ionization energy, electron affinity, and an electronegativity scale that was founded on thermochemical data. Electronegativity generally increases from left to right in a row on the periodic table and decreases going down a column.
When drawing Lewis structures, there are some rules to follow that make the process a lot easier. First, sum the valence electrons from all the atoms, taking into account the overall charge. Second, write the symbols for atoms, which shows which atoms are attached to which, and connect with a single bond. Third, complete octets around all the atoms bonded to the central atom. Fourth, place any leftover electrons on the central atom. And fifth, if there are not enough electrons to give the central atom an octet, try multiple bonds. When making Lewis structures, there are multiple arrangements that can be used to still achieve the octet. To figure out which is best, look at the formal charge. A formal charge is the charge an atom would have if each bonding electron pair was shared equally between the atoms. When calculating formal charge, all unshared electrons are assigned to the atom on which they are found, and for any bond, single, double, or triple, half of the bonding electrons are assigned to each atom in the bond. Formal charge is equal to the number of valence electrons minus the bonding electrons times 1/2 minus the non-bonding electrons. When picking the correct Lewis structures, remember that the one with the formal charge closest to 0 is most likely the one that is your dominant structure. Also, the formal charge is not the actual charge of your atom.
Sometimes a single dominant Lewis structure is inadequate to represent a particular molecule or ion. In such situations, we describe the molecule by using 2 or more resonance structures for the molecule. The molecule is envisioned as a blend of these multiple resonance structures. Resonance structures are important in describing the bonding in molecules such as ozone, O3, and the organic molecule benzene, C6H6.
Here we have the resonance structure for ozone, or O3. Ozone's structure is a resonance hybrid of the 4 canonical forms. Here we have benzene's resonance structures. Benzene's structure is a resonance hybrid of these 2 forms. octet rule is not obeyed in all cases. Exceptions occur in the following scenarios. 1. When a molecule has an odd number of electrons. 2. When it is not possible to complete an octet around an atom without forcing an unfavorable distribution of electrons. And 3. When a large atom is surrounded by a sufficiently large number of small electronegative atoms that it has more than an octet of electrons around it. Lewis structures with more than an octet of electrons are observed for atoms in the third row and beyond in the periodic table. The strength of a covalent bond is measured by its bond enthalpy, which is the molar enthalpy change upon breaking a particular bond. Average bond enthalpies can be determined for a wide variety of covalent bonds. The strengths of covalent bonds increase with the number of electron pairs shared between two atoms. We can use bond enthalpies to estimate the enthalpy change during chemical reactions in which bonds are broken and new bonds are formed. The average bond length between two atoms decreases as the number of bonds between atoms increases, consistent with the bonding being stronger as the number of bonds increases. Because it is difficult to show chemical bonding via a lab procedure, we decided to use this molecular structure model kit to depict ionic and covalent bonds. The covalent bond we focused on was CH4, or methane, and the ionic bond we focused on was NaCl, sodium chloride, or more commonly known as table salt. The first molecule we focused on was CH4, methane, which is covalently bonded. The black atom, carbon, is covalently bonded by the white sticks to the 4 pale blue atoms, the oxygens. Because they are all nonmetals, this is a covalent bond. The atoms share their electrons but exhibit no polarity, as the electronegativities of the carbon and hydrogen are nearly identical. If the electronegativities differed, the bonds would be polar covalent, like in an H2O or water molecule. As you can see, the 4 oxygen atoms are bonded to the carbon in this ball and stick model. Now we will do a ball and stick model for NaCl, or sodium chloride. Here we have Na, which has 1 valence electron it wants to give away, making it eager to react. On the other side we have Cl, which has 7 valence electrons and wants to gain 1 more to fulfill the octet rule. It is also eager to react, and therefore joins with sodium in an ionic bond, where the valence electron is taken from Na and given to Cl, resulting in Na being a positive ion, or cation, and Cl being a negative ion, or anion. Because of the equal difference in positive and negative, they are attracted and join each other in an ionic bond, shown by the yellow stick.
Sweet.
And then, so close. Why are you laughing? Why are you laughing? Look at the camera.
2 or more
Items.
Chemical bonding is the bonding of 2 or more items.
Chemical?
No, I said wait for it because I knew the wind.
Let's jump in.
Jump.
2, 3, let's jump in. Let's jump in.
I'm gonna tell you guys how I study this chapter. For this chapter, you're not even doing it anymore. Why are you doing this to me?
You should practice it. Keep practicing it.
No.
Just practice. See, I'm recording.
No.
2, 3.
When making the correct.
Energy required to I'm sorry. Mole of an ionic compound into its gaseous ions. Bonding. Ionic substances result from the not the. Where's the? Oh, it's still going.